Okay. All right. So I don't have any slide. So I just use Microsoft Word to explain. So today will be the topic second order. So this is Wednesday, 27th April 2022. All right. So just to revisit what is going on, or what is the current topic, current activities in this subject, we recall back the first order. So if you recall back the first order, you have the standard form K over tau S plus 1. And then based on this standard form, we have the inverse Laplace, where normally the inverse Laplace in the form of the y equal to Km 1 minus exponent negative t over tau. So this is the standard inverse Laplace for the first order. The main reason we develop the first order because we have the ready-made inverse Laplace. So this inverse Laplace normally have the response. The purpose of having the inverse Laplace in order to solve the problem, to obtain the value which we'll plot for obtaining the desired response. Normally, we will employ the step input. So this is what we call it, step input. So the change based on the magnitude m. So whenever we have a step input, then we will have the typical response of the first order, which is increment, and then it reach the steady state. So this is the output response for typical first order process. So meaning that whatever we have, once we construct the first order, this is the kind of response that we will be obtained. There will be no other pattern, only this pattern, if we have the first order. Now, if we go further for the second order. So the problem is in the second order is they have a different category. First of all, we have the form K over tau square S square plus 2 psi tau S plus 1. So you have the damping coefficient. This damping coefficient will determine which category of the second order. So when you have the damping greater than 1, it is overdamped. Damping equal to 1, you will have the critically damped. And lastly, the damping less than 1, between 0 and 1. So this is what we call it underdamped. So based on the last Monday, I already introduced to you how to obtain the second order. So from the second order, we obtain the transfer function. Then what we need to do next is to classify the class of second order for the purpose of obtaining the inverse Laplace. So in this case, the damping coefficient according to the value of damping, the value of the psi. Note that the damping cannot be negative. It's like a time constant. So the minimum value should be 0.01, and it also cannot be 0. So that's why you have 0 less than damping less than 1. It's not lesser than or equal to. It's just less than. So the damping cannot be 0 or negative. So this is the criteria for the damping. Alright. So far, in this case, all of input that will be used is based on the step input. This is the fixed type of the input where we will use the step. Why we are using the step? Normally, either when we operating something, either we decrease the value or we increase the value. And this value, we assume there will be no, it will be spontaneously changed, automatically changed. Let's say now it's 4 meter cube per hour. You want to change to 6, it's automatically to 4 to 6. Because we are in the digital hour now, digital era. So the change is spontaneously. So that's why either you have the step input based on the magnitude, positive or negative. So this is the fix. The same goes to the first order or second order. We will use the step input. And also in the chemical industry, it is widely used, the step input. So this is the thing that is generally acceptable in the chemical engineering area. Do we have another input? Of course, we have it, but in this case, we just focusing on the step input. All right. Now, if I take a look on the bigger picture, just a typical response for the process. So let's say this is your steady state increment and then it reach. So let's say this one is based on the first order. Now, how we can obtain the other process? All right. So normally, we have covered the overdamp and critically damped. We start with the critically damped first, where damping equal to 1. So when you have a damping equal to 1, this is your response. Where the response actually similar with the first order. So first order or critically second order, critically damped. Normally, for the critically damped, if we take a look, why we have the similar profile. All right, so let's take a look on the example. Let's say for the first order, you have GS equal to 2 over 5S plus 1. So this is the first order. For the second order critically damped, the transfer function should be 2 5S plus 1 square. Meaning that the only change is on the denominator, where currently you have 2S plus 1. Where this one, it become 5s plus 1, 5s plus 1. So when we have the similarity in terms of the denominator, then it will provide like the first order response, as long as the tau is similar. In this case, the tau is 5s plus 1 and 5s plus 1. So in the end, the response is look the first order. This one is applicable if your gain and the tau is similar. So this is the typical response of second order critically damped. And then for the overdamp, normally your denominator have a two different tau like this. So this is second order overdamp. Automatically we can say overdamp because you have two different tau value. This is 5, this is 3. So if we want to find the roots, negative 1 over 5, negative 1 over 3. So you have two different roots. Automatically it's unequal root, which contributing to the overdamp response for second order. So when you have the overdamp, that means the damping will be greater than 1. So what is the effect of damping greater than 1? Normally, when you have the damping greater than 1, your process becomes slow. Slow of what? Okay, it's like this. So let's say we start at the same point. This is your response. Slow to achieve the new steady state value. So it will take a long time to reach the final value compared to the first order response. So this is the effect of having the damping greater than 1 or under the class of overdamp. So compared to the critically damped, overdamp response will have a slow reaction, slow response to achieve the final steady state value. The greater the damping factor, then the process becomes slower. The response becomes slower. So this is the kind of response that we want to observe. Now, so we already complete the critically damped and overdamp. So here what we can observe on the second order critically damped is the equation, the denominator. Both of the denominator, if we take a look, can be factorized. So when you can factorize it, you can obtain the two roots where we normally have what we call it real roots. So you can solve based on the, for example, let's say you have 15s squared plus 8s plus 1. So this one automatically you can factorize it like this. Or sometime maybe for this case you will have two different tau. And sometime maybe you can have 16s squared plus 8s plus 1. Where this one contributing to the 4s plus 1. 4s plus 1. So this is the equation or the mathematical model that can be factorized, which contributing to the similar root or unequal root. So in some cases, there maybe the equation cannot be factorized. For example, 16s squared plus 2s plus 1. If we try to factorize it, maybe you will get the complex number as your solution. So when the equation cannot be factorized, then automatically it is under damped response. How do we know? Okay, let's prove it. So we have the K over tau square S square plus 2 psi tau S plus 1. So now we try to compare this one, where the tau square equal to 16, tau equal to 4. And then 2 psi tau equal to 2. 2 psi multiplied by 4 equal to 2. So you get damping equal to 2 over 8, which is 0.25. So this indicates that the value of damping obtained is 0.25, which is under category of underdamped. So this one is what we call it qualitative analysis. If we take a look the equation, we observe, we analyze. Is it the equation can be factorized or not? If can be factorized, do we have a same tau? If we have the same tau, that means you have the same root. Then it is under category of critically damped, where the damping equal to 1. Another case, you're able to factorize the equation, but you have two different roots. So when you have two different roots, then automatically your damping will be greater than 1, which is under category of overdamp. And last case, if you have the second order, but you cannot factorize it. If you try to factorize it, then you may get complex conjugate number. Now, this is the underdamped response. So that is how we can differentiate our equation actually. How to classify it under the overdamped, critically damped, or underdamped. So if we try to see the response, since it is underdamped, you have the conjugate number or complex number, then the response is a little bit weird. Weird in terms of what? You will have like this. So this is what we call it oscillating. When the value is up and down, then what we call it oscillation. It's complete one period of the time to complete one circle or to complete one cycle. So this is what we call it underdamped response. So this is the last class of the second order, which is underdamped response. So where in the underdamped response, normally we will have the oscillating response. Okay. Now,
Doctor.
Yeah.
May I ask for the graph, right? For the y-axis and x-axis, what is the name of them?
The y here is the output, and the the x-axis is the time.
Okay, understood, doctor. Thank you.
Normally, the output, what is the kind of the output? Sometimes we have the temperature. So the temperature behavior for second order can be in the form of the first, sometimes can be in the form of the oscillation, depending on the damping factor value. So here the Y can be level, can be composition, or concentration, and temperature. So this is the thing. the common variable that will be used. How to get that variable is from the conservation mass principle, either overall mass, component, or energy balance. So this one, if we take a look, is a long journey. You have the process, you do the derivation, you do the Laplace, and then you obtain the transfer function. Then you classify first order, second order. If first order, you proceed with the inverse Laplace. If the question asks you, give you multiple tank, then in the end you will get second order. So second order, you further classify based on its damping coefficient. Either it is overdamped, underdamped, or critically damped. So lastly, this is the kind of response. Once you calculate the value against time, you plot, you get this kind of response. So that is the main idea of the mathematical model for this subject. So normally, the question relating to the underdamped is very popular to be asked during the final exam. So why? Okay, let's take a look why we have so many, or this term become too popular. Because when we have the oscillation, then we have different characteristics to be considered. So let's again. So this is our typical response. And then we have the graph. So this is the output variable. So based on this is the oscillation pattern for underdamped response. If we take a look, although it is oscillating up and down, but still in the end, it reached the steady state value. So this is the value of the steady state. So meaning that at the final time, it still maintained at the final value. Only the problem here, it is oscillate up and down, which is sometimes is undesirable. So for the second order, there are some characteristics that we need to consider. This one, you can refer more on the chapter 4.4. Page 69 on the third edition textbook. So what is the characteristic? All right. So in this case, we start from the left to the right. So here, let's say this one is the Y and this one is the T, where the Y is the output variable. Our starting point will be here. So this is our starting point. The initial value. So this is the initial value. So once we operate the process and then you get the response, okay, here it will start to increase. The response start to increase until it reach the dash line here. So when it reach the dash line, this mark the first time the process reach the final value. Here, this point represent what we call it the first time it reach the final value. The final value is this one, the Y final. So here, the Y final is operate at this one. So at the end of time. But since the process is oscillating, so that is the first time it reached the final value. Although it cannot be sustained. it keep increasing. So this point represent what we call it TR, where TR represent the rise time. The short form is TR, the rise time. So we have the formula to calculate the TR, where the TR equal to tau divided by 1 minus psi square. In bracket, pi minus inverse cos psi. So this is the formula to calculate the rise time. Where you can refer equation 460. So in this case, since we know that this is the underdam, so on the underdam we have the value of the tau of the psi. So we just include the value of the tau and the psi inside the formula. So to obtain what is the time required for the process to reach the final value for the first time. So that is what is meant by the rise time. So once it reach the rise time, that it keep increasing. And it keep increasing until it reach this point. So this is what we call it maximum value. This is the highest point of your graph. So when you reach the highest point, then it represents the maximum value that the variable can obtain. So this maximum value is happen on what we call it TP. So what is the TP? TP represents time to first peak. TP. Time to first peak. The time needed to reach the maximum value. So since this one is like a mountain, and then this is what we call it first peak. First peak. And then this one is what we call it second peak. And last, you have another peak, the third peak. So we count it, the first peak, second peak, third peak. As long as the value exceed the final value. So you have kind of the peak over there. So the time to the first peak can be calculated using TP equal to pi tau square root 1 minus psi square. So this is your time to first peak. And then in this case, we have what we call it the overshoot. Overshoot. So what is mean by overshoot? How much the value is exceeding your final value. So in this case, we have two different points. So the first one, this to here. So this is what we call it A. And lastly, this point. B. So the A is the value that exceeding the final value, and the B is the interval between the initial value to the final value. So the ratio of A and B is what we call it overshoot. Overshoot. Where overshoot, short form is OS. And it can be calculated as the A over B. Where the A, the maximum value minus the final value. And the B, final value minus initial value. So this is the definition of the overshoot. Maximum value minus final value divided by final value minus initial value. So that is the overshoot. So this one, if we take a look, is based on the value from the graph. And another way to calculate the overshoot is by using the tau and the damping coefficient, where the OS also can be calculated equal to exponent negative pi psi divided by 1 minus psi square. So this is the formula involving the value of damping coefficient to calculate the overshoot. So the overshoot represent how much your process or the variable or the value exceeding the steady state value. And then in order to measure the severity, or is it to consider the oscillation is acceptable or not, here we will take a look on the second peak and the first peak, where we want to see how much the decrement of your magnitude from the first peak to the second peak. Let's say from the A, you get around 10 meter. And then for the second peak, it's around 1 meter. So there is a drastically change from in terms of the magnitude from height of the first peak into the second peak. So how to measure that is to call it the decay ratio, where here it will consider the A and here this one I put C, the height of the second peak. So the one is what we call it decay ratio. Or dr, where the decay ratio is obtained by the formula exponent negative 2 pi psi divided by 1 minus psi square. Or you can obtain it from the formula. dr equal to C over A, where the C is this one, the height of second peak divided by the height of the first peak. So that is the decay ratio, how much the value will be decreasing as based on the peak measurement. And lastly, since we have the oscillation, so the term or the definition of the oscillation means the complete cycle of the response. So for this, we categorize it. Let's say you have starting point here. This is your starting point. So it will go to this one until it reach the final value point. So this is what we call it period of oscillation. period of oscillation. So where if we complete one cycle of your response. Since you start at the final value, you finish at the final value. Or sometimes we can measure based on the peak. We can start it from this peak, the maximum value at the first peak, and it will go down, and then it will go up again to the second peak. So this is also called the period of oscillation. So this period of oscillation can be determined based on the time. So you minus the time, then you can get the period of oscillation. How long it will take to complete one cycle of response. So this cycle can be either start from the final value to the another final value, or the first peak into the second peak. So that is the period of oscillation. So this is the characteristic that is commonly asked for the underdamped, which may consist the rise time, the time to first peak, overshoot decay ratio, or the period of oscillation. So it's not surprising why this question or this topic is so popular during the final exam or test. Luckily for you, since we have the test in the weeks number 6, so it's not covered until to this point. Before this, the previous semester, the second order this has been covered. So this is the explanation of the second order underdamped response. So this is that's just the brief discussion or brief explanation. And lastly, of course, we have all of the term, all of the characteristic involved in the second order underdamped response. And lastly, the inverse Laplace. So for the inverse Laplace, normally is quite complicated. For underdamped, you have a long equation to be solved, where you have the yt equal to km bracket 1 minus exponent negative psi t over tau. And then you have the cos 1 minus psi square over tau t plus 1 minus psi square. So here it involves the sinus and cosinus. So that's why it's a little bit long equation. So this equation, you can refer to the equation number 451, page 67 in the 3rd edition textbook. All right. So that means in this case, when we employ the underdamped inverse Laplace response, if we put the value, then this due to the cosinus and sinus, in the end, you will get the oscillation response like this. That's why the equation is complicated, because you want to represent the desired process. Okay, so I open to any question that you may have before we start doing the exercise. All right. So now let me find suitable exercise for you. Meanwhile, we can take a break for 5 minutes if you want before while I'm finding the right question for you.
Doctor, can you show the formula first
Formula what the which formula?
under them? The
Under
YT.
them. Okay. Okay, this one. Okay, we can use the exercise in our textbook. So for the exercise, exercise 4.14. 4.14 and 4.15. Page 75. Is based on the third edition textbook. Those have the third edition textbook, you can refer to this question. For the new textbook, I think we have the equation, only we need to find the proper equation. Because I think the chapter is a little bit different. All right, in this case, let me try to find the question. Okay, I cannot find the soft copy of the question. So I hope you can find the exercise 4.14 and 4.15, page 75, third edition. So in this case, here the question relate to the step change from 15 to 31 psi in actual pressure. Results in the measured response from a pressure indicating element shown in figure E4.14. So for the E4.14, the figure looks like this. Where the response start from this. Okay. And then 12.7. .2 and 8. And then we have this one. So if we take a look, this one is 2.3. Okay, in this case, let's revise a little bit the question. The question wants we to find the R prime S P prime S equal to K tau square S square plus 2 psi tau S plus 1. All right. They want us to find the K, the tau, and the psi. The gain, the time constant, and the damping coefficient. Once we obtain that, then we include inside the equation. So we start with the K. So what is the formula for the K? For determining the value of K? Where the K is the process gain. So normally for obtaining the K is based on the delta output over delta input. So this is the standard formula for obtaining the value of process gain in the second order or the first order. It's the same thing. First order, second order, the K will be calculated using delta output divided by delta input. So in this case, which one is your output? So this graph represents your output. So this is your output. So based on the graph, your R is your output. So in this case, the delta output means the final value of your output minus the initial value, where the final value locating at this point. So this is your final value at the final time. And this is your initial value. So meaning that data output equal to 11.2 minus 8. And your input, normally whatever the input is based on the step change, step input. So here the step input has been given in the statement. A step change from 15 to 31 psi. 15 to 31. So that means 31 minus 15. 1, 5. So we include the delta output over delta input value inside the equation. So you can calculate the value of the gain. So what is the value of the gain?
.2, doctor.
0.2.
Yeah.
Do we have another answer?
No, doctor. Same.
Same, huh? Okay, thank you. All right. If you check to our WhatsApp, you also can download the question. Thank you for contributing to the screenshot. So here is the K. We already have the K value. Now, based on our transfer function, this K is done. We know that. Now we want to obtain the tau and the psi. So how to obtain the value tau and psi? So we take a look. What formula do we have? Now we already use 11.2. We have the 8. So this one 2.3. 2.3 represent the period. So 2.3 P equal to 2.3. So based on this, equal to 2.3 equal to, the formula is 2 pi tau divided by 1 minus psi square. So technically we have the formula, we have the value. But the problem here, we have two unknowns. Tau, we don't know. Psi, we don't know. So we cannot solve the problem. So we need to take a look on another variable or another value that can be used to solve our problem. So we already used the 2.3 and lastly 12.7. So this one is we don't use it yet. So based on this, if we refer back, this represent the this one is A. And then the starting point, this one is B. So when you have this distance, it represents the overshoot. Where the overshoot, we know that A over B. A is the magnitude of your peak and the B is the magnitude of your increment from initial to final value. So we can calculate the overshoot. So overshoot, OS equal to A over B, where the A is 12.7 minus 11.2. Divided by 11.2 minus 8. So from this, we can obtain the value of the overshoot. So please calculate it.
Zero point 0.47.
0.47. Okay. Anybody get the same answer? Or
Yes,
any
sir.
disagreement?
Same, sir.
Same. All right. Then
Same
if
answer.
same, Okay, thank you. If we same, then we are in accordance to the right direction. So here, what we can do with the value of 0.47. So in this case, we need to relate the formula. So here, the overshoot has the following formula. Exponent negative pi psi divided by 1 minus psi square. So this is the formula of overshoot. So based on this, we have the value of 0.47. We know the value of pi. Pi is 3.143. It's a fixed value. Then in this equation, we only have one unknown, which is the damping. So we can solve the value of damping coefficient. So please use your calculator to find out what is the value of the damping which contributing to the overshoot 0.47. Any answer?
Zero point two three, doctor.
0.23. Okay. So this is the damping coefficient value 0.23. Since this is the underdamped response, the value must be between 0 to 1. So now you have 0.23, which is in accordance to the range of under damped response. So we have the damping value, and lastly, we can substitute our value. This value here can be substituted into this one. So we have the damping value, then this one, the period is 2.3. We know the pi. So now we can obtain the time constant tau. So that means you have one equation and one variable. So the degree of freedom should be 0. So automatically you can get the tau value. Okay. Any value for the tau?
0.36.
0.36. All right. So we have the K, the tau, and the psi. And of course, in the end, we can substitute into our equation here. Add R prime S, P prime S equal to K is 0.2. And then you have the tau 0.36 square. To psi 0.23, 0.36 S plus 1. So this is the solution for question 4.14. Any question relating to this problem? All right. I think we can notice the mood is slightly lower. Okay, for this part, please continue with the question 4.15. If you having a difficulty on solving a question 4.15, then you can send your exercise to me for checking. So I think it's already 1:37. So that is the end of second order response. And of course, the second order will be asked in the final examination. For that purpose, I will give you the exercise later on. The exercise relating to the question paper of final exam, the standard paper for standard question for the final exam for you to try. And for this opportunity, since this is our last class before midterm break and before the Eid celebration, I would like to say I'm sorry for any kind of the misdoing or lack of explanation or the other inappropriate attitude from me. So I really apologize for that, and I also wish you a good celebration after 2 years of MCO. I hope we can have a better celebration this year. So with that, thank you very much for your attention again, and have a nice holiday and midterm break. So class is dismissed. Thank you very much.
Thank you, doctor.
Thank you, Doctor.
Thank you, Doktor. Selamat Hari Raya.
Thank you, Doktor. Selamat Hari
Thank you,
Raya, Doktor.
Thank you, doctor.
Thank you, doctor.
Okay, selamat hari raya.
Selamat Hari Raya, doktor. Thank you, doctor.
Thank you.